Hello everyone, welcome to our class ECE212 Electronics 1, and this is Electronics Devices and Circuits. So I am your professor. I am Engineer Handel Del Serna Magnano. You can call me Sir Dil. So this is my background class to just give you a basic idea of who is your professor in this class. Alright, so I am a Master of Engineering in Telecommunications. I finished this at the Asian Institute of Technology in Pathum Thani, Thailand. And I also have a Master of Science in Teaching Mathematics, 42 units at the University of Cebu, Philippines in 1997. And also I graduated two Bachelor of Science in Engineering. One is in Electrical Engineering, and the other one is the Electronics and Communication Engineering. So both of them were done at the Cebu Institute of Technology, that is now called Institute of Technology University. Okay, so today we'll talk about basic thing about electricity, current electricity, uh, especially Ohm's law. But before we go to the details of this topic, so let us have first the objectives of our discussion for today. So at the end of the lesson, the students, meaning you, so the students will be able to learn Ohm's law and the basic concepts of electricity, determine the direction of electric current flow in a circuit, learn about the different sources of electricity, understand the basic concept of electronic machinery devices, learn about resistor and its purposes, know the factors affecting resistance, and know how to calculate resistance, and then learn about resistor color coding to determine the resistance of a resistor. Okay, so here's the basic concept class about the electricity. We have what we call electric current. So electric current is a measure of the amount of electrical charge transferred per unit time. So the time usually is in terms of seconds, and it represents the flow of electron through a conductive material. And mathematically, this is given in this equation class. I stands for the current, and delta Q, that is the charge, the change of charge, and delta T is the change of time. Okay, so electric current is just similar to a current of water, but electric current flows is solid metal wires, so it is not visible. So I repeat, electric current is similar to a current of water, but electric current flows in solid metal wires, so it is not visible. So electric current can vary a lot of power. Okay, so one of the purposes of electric current, like for example, if you have an electric saw that cuts a log in 10 seconds. Okay, so usually we have this handsaw cuts a log in 5 minutes, but now using electricity or using the electric current, so we can shorten the duration of doing a cutting job. All right, so that's one of the purposes of the electricity or the current. Electric current exists whenever electric charges flow through a region. For example, a simple light bulb, simple light bulb circuit, as you have seen here in this illustration. So the magnitude of the current is measured in amperes. No, amps, or you can use the unit A. A stands for amperes, or we can also use the amps as the um, abbreviation of this word amperes. And take note that 1 ampere is equal to 1 coulomb per second. Okay, so this is a very important concept, class, so you have to remember this. So we know that current, electric current is the change, no? Electric current represented by I is equal to the change of the charge per unit time. Okay, so we have, as mentioned earlier, I equal to delta Q divided by delta T. So that is coulomb. Coulomb, the charge, the unit of charge is coulomb, then per second. So for example, we have here an illustration. So we have a positive, we have this light bulb. Okay, so in this case, so we have positive connected to the bulb. So what will happen? So of course, because for the current to flow, there should be a closed circuit. Okay, so it won't flow, and also this one won't flow. But this one, since there's a, a complete circuit, so because this is positive part of the battery, this is the negative part of the battery here. So positive connected to the negative, so now the electron will flow. So there will be light in the bulb. But in these two cases, so the light will be off. Okay, so for this one, the light will be, it depends, no? There are, but usually, the basic concept here is that if there is a complete circuit, then, and there will be a force, like for example, the battery, that is an example of electromagnetic force or electromotive force that will push the current or the electron to flow into the circuit, and that makes the valve lights up. So electric current circuits. An electric circuit is something that provides a complete path through which electricity travels. So that's what I mentioned a while ago. So in order for the light bulb to be lighted, so there should be a complete path through which electricity travels. Otherwise, there will be no light in the bulb if there's no complete path, like shown in the three picture here. No? There's no complete path here. So in this case, so if this is there's no complete path from the source up to this light bulb. So in these two cases, so the light will not be on. In this case, there will be a complete path of the electrons, electricity. So light will, or bulb will light up. So this part, class part C, could be represented in this what we call circuit. Okay, so this is a basic electric circuit. So we have here the source, and take note, class, that the current flow in this illustration, so you have to remember that the current flow from negative to positive. Okay, so this is the direction of the flow of the current. So that's why here we have the arrow in this direction. So it flows from negative to positive, and it will uh, completely flow in this circuit. And when the current or the electricity or the charge uh, will will flow into this circuit, so we will have the device, which is the valve, will light up. Okay, so we have here the circuits and current as we have here the setup, no, of a basic circuit. We have here the switch. All right, so we have here the positive part of the battery, the negative part of the battery. So it is This terminal here is connected to one part of this bulb, okay, and the other end is connected to this part of the bulb. So now, because of this is a force class. This is a force that will push the electrons to flow into the circuit. So when electrons flow, or the charge flow into the circuit, so this valve will light up. Okay, so in this case, if you look at this, the switch is on. So meaning there's a closed path, closed circuit, or the path is closed, because this one is before this bring brought down. So when this is open, so there will be open. Okay, so when this one is push up, so it will be open, so the circuit is open, so there will be no current flow. So like in this case, okay, so in this case, no current flow because the circuit is open. So this switch is open. Now when you bring the switch down, so when you bring the switch down, so in this case now, so the circuit already closed, so there will be a flow of the current. Okay, so the direction of the current will be from negative to positive, so it will be flowing like this. Okay, so that is the flow of the current. So we use I to represent the current. Okay, then we have what we call voltage. So what is voltage? So voltage is the electrical force or pressure. So that is electrical force or pressure that causes current to flow in a circuit. So we know that uh, the conductor has an electrons. So when a force is applied, or the pressure is applied, or an electromotive force is applied, so the current will be pushed and then it will travel throughout the circuit. So voltage is the electrical force or pressure that causes current to flow in a circuit. And the voltage is measured in terms of volts, and the symbol used is V. Voltage difference, no? A voltage difference of 1 volt means 1 ampere of current, thus 1 joule of work in 1 second. So it means, class, to have a 1 volt, we have 1 ampere of current that will do a certain work that is in joules, no? 1 joule of work in 1 second. Okay, so to understand it, this is the analogy, class. So it's just like we have a fluid here in this container, and we have a stopper here. Now when the voltage is applied, it's just like you are pushing, no? You're pushing the fluid out of its container, so it will go like this. So you see, from where the the pressure is applied, so this is where the negative part. Okay, so that's why we have the negative here, and this is the positive here. So it means that current will flow from, or the movement, no, in this case the movement of the fluid is from here towards there, so from negative to positive. So similar to the voltage, so we have here the positive part of the battery, or the pressure or the electromotive force, and this is the negative part. Okay, so the current flow will be from negative, no, from negative to positive. So it will flow like this, it will flow like this. So this is our current I. So remember that, no? Current flow from negative to positive. Okay? And we have what we call electrical resistance. So when we speak of resistance, that is the something that will oppose, no? Oppose the flow of the current. Oppose, it's a resistance is something that will oppose the flow of the current. So resistance measures how difficult it is for the current to flow. Okay? So the total amount of electrical resistance in a circuit determines the amount of current that is that in the circuit for a given voltage. The total amount of electrical resistance in a circuit determines the amount of current that is in the circuit for a given voltage. So I think this is that is in the circuit for a given voltage. So the more resistance the circuit has, so the less current that flows. Okay, so the more resistance the circuit has, the less current that flows. Okay, so SI unit of resistance is called ohm, and this is the symbol of ohm. No, this is the omega. So this is the symbol of ohm, omega. All right, 1 ohm is the resistance when a voltage of 1 volt is applied with a current of 1 ampere. Okay, so it says that 1 ohm, we have the resistance equal to, or 1 ohm is means equals is the resistance when voltage of 1 volt is applied with a current of 1 ampere. So in mathematics, so this is expressed as R equal to V over I. Okay, so when you're asked to find the resistance, then if you know the voltage, you know the current, so you will be able to calculate the resistance. Or from the basic concept, we have V, or the voltage is just the product of the current and resistance. Okay, so V is equal to IR. All right, so we have here an illustration of the statement here. So we have 1 volt, right? So 1 volt, we have 1 ampere. So we have the resistance 1 ohm. Okay, so 1 ohm. So it means that if you are given 1 volt, okay, so 1 volt, unit of volt is V, and 1 ampere. So we have a resistance that is 1 ohm. Okay, so 1 ohm. So that is what is meant by this statement here. Okay, then we have here what we call Ohm's law. So this is a very important law class. We speak of voltage, current, and resistance. So the one that developed this law or established this law was called George Simon Ohm, born in 1787 and died in 1854. He's a German. He was a German physicist. Discovered Ohm's law in 1826. So here's the statement of Ohm's law. So the current through a conductor is proportional to the potential difference between its ends, provided the temperature of the conductor remains constant. Okay? So the condition here, class, is that the temperature, no? Temperature of the conductor remains constant. Otherwise, so this one uh, will not work, no? This law. So that is the condition here. So the current through a conductor is proportional to the potential voltage difference between its end, provided the temperature of the conductor remains constant. Okay, so we have electric potential difference V, right? We have here the electric current represented by I. Then we have here electrical resistance. So Ohm's law says that R is just the, I will rewrite this one, class. The equation is R is equal to, as I have written a while ago, the voltage divided by the current. Okay, so this is what we call Ohm's law. So this is a constant resistance, right? So this is a constant resistance. Otherwise, the resistance will not be the same. When the temperature increases, so that changes also the resistance. Okay. George Ohm showed that the flow of an electric current through a wire depended on its resistance and the potential difference between its end. Okay. So depends on, but typically in what we have seen a while ago, so normally from negative to positive, or from positive to negative. So because the positive electron will be attracted to the negative electron. But if you look at the symbol, if you have a circuit something like this, so usually the for the battery symbol class, the longer side, that means plus, and then we have the negative. Okay, so we have here a simple circuit, okay, with a resistance R. Okay, so current will flow if there's a complete circuit. So if you look at the arrow something like this, we have the I. So it's like that, from positive it goes to negative, something. So the positive electron will be attracted to negative. Okay, so from positive to negative. Or if you start from here, so it's just like from negative to positive. Okay, so as mentioned in the concept of Ohm's law, so the voltage is proportional to the current. Okay, so proportional to the current. So it means that V divided by I is constant. When you divide V by I, so you will have a certain constant. So, and that is what we call the resistance. So a graph drawn between the voltmeter readings and ammeter readings shows a straight line pattern. So the straight line indicates a relationship and is named as Ohm's law. So you see here, there's a straight line. So the assumption here is that the temperature is constant. Okay, so you will have this linear, no? linear graph. So we have the voltage on the horizontal axis, and we have the current of the uh, vertical axis. So this is an example of a nichrome wire. We have the voltmeter here, we have the ammeter, and this we have the variable source. So it means variable class. If you can see an arrow, this is the symbol of battery or the source voltage. So it means it's variable. Okay, so we have resistance and resistors. So the ratio of voltage to current is called the resistance. All right, so we have R equal to V divided by I. So it means if you have 1 volt of pressure, or 1 volt of electromagnetic force divided by 1 ampere of current, then you will have a resistance of 1 ohm. Okay, so mathematically, when you use your algebra, you multiply both sides by I, so we'll get V equal to IR. Product of, so voltage is just the product of the current and the resistance. In many conductors, the resistance is independent of the voltage. In many conductors, the resistance is independent of the voltage. This relationship is called Ohm's law. Okay, so we have here an illustration of a circuit. We have the source voltage here. Okay, this is a variable, so if you can see the arrow here, okay, and then you have the source voltage, so it means that our source voltage is is variable. So we can increase it, we can decrease it. So that's the meaning of this class. If you have the source voltage, we have plus minus here. Then you have the arrow, so that indicates that our source is variable. So we have a variable source of power supply or voltage supply. Then you can measure the current using your ammeter, for example. So A here for ammeter reading. So if you have the ammeter, so you will be able to measure the current flow. You just attach. So from this terminal here, from the positive, then you connect uh, one end, no? Because this is a closed circuit class. Okay, so this is our circuit. Then you will be able to read the current. So you have the resistor, you have the source voltage, and you will be able to measure the current that is flowing into the circuit. And now when you want to measure the voltage, so you can put the terminal of your voltmeter, okay, and then you can measure the voltage across this resistance. All right, so we have a current reading here because there will be current that will be flowing in this circuit. So the current is I. Okay, so by the Ohm's law, so when you multiply the current and the resistance of this resistor, then you will be able to get the voltage, right? So from this equation, you'll be able to get the voltage. Okay, so that is expected that the voltage that you will get is just the product of the current, whatever is the current, that is the reading of this ammeter here, multiplied it by the resistance, then you will be able to get the voltage. And you can check that one. So by the principle that the voltage is the product of current and the resistance, then when you do the actual reading, so perhaps it could be different, no? It could be a little lower. In reality, the voltage reading here is a little lower. So what is the reason is that normally the voltage source has its internal resistance. So when there's an internal resistance, so there will be a voltage drop. So that's why the voltage that you will see here in the reading would not be equal to uh, whatever we expect now, because we expect the same voltage here, but because of the internal resistance there would be a voltage drop, so it would be less than this source voltage. Okay, so we have what we call electrical resistor. So what is a resistor? So resistor is used to control the amount of current flowing in a circuit. So that's its function, no? That's one of its purposes, to control the flow of current in a circuit. So electrical components called resistors can be used to control current. And there are two main types of resistors. So we have what we call wire wound, or we call coil of fine wire resistors. And we also have the composition, that is a carbon resistors. Okay, so whatever type of resistor is that, so we have the same calculations class. Okay, so the symbol for the resistor, for a resistor, is something like this. It's just a straight line, then you have a crooked line, and then a straight line again. So that symbol represents a resistor. So physically, this is what you will see. This is an example of a resistor. So when we draw a circuit that involves a resistor, so you can change that into this symbol. And we have what we call electric resistance. So what is this electric resistance? It's the ratio of 1 volt and 1 ampere. And that ratio is called ohm, 1 ohm. Or we can say that ohm, or 1 ohm, is the unit of electric resistance. So 1 ohm is equal to the ratio of the voltage 1 volt and 1 ampere. So that is ohm, 1 ohm. And this is symbolized, or when you write ohm, so instead of writing the word ohm, so you can put the symbol omega, Greek symbol omega. Okay, so Ohm's law gives a relationship between the voltage V, current I, and resistance R as follows. So V is equal to I times R. So when you're asked to solve for the current, you just divide both sides by R. So from here, when you divide this equation both sides by R, so the R on the right side becomes 1 because R divided by R is 1. 1 times I is I. Then the left side we have divide this by R, so we have V over R, or you just replace the position. So we have I equal to V over R. So the current here, I, the unit is in amperes, and the voltage here, the unit used is volts, and the resistance here, the unit used in resistance is ohms. So here's the uh, equation. So when you have I equal to V over R, it gives you the current. So voltage and resistance must be known, or if you know the voltage and resistance, then you will be able to calculate the current I. Or if you have known the current and resistance, you just multiply them. No? Current and resistance, you multiply, you will get the voltage. Or if you are asked to solve for the resistance, so you must know the voltage and current. So using this ratio, V divided by I, or voltage divided by the current in amperes, so you will be able to find the resistance. But take note, class, this true only for the constant temperature. All right. Okay, so I would like to thank the source of this material. So they're called iTutor. No? It's a very simple way of explaining Ohm's law, the basic concept of electricity, current, voltage, and resistance. So this is a very useful materials that I use in our lecture. So if you want to know more details about them, you can use or you can visit this link, no? www.itutor.com. Okay, so if you want to call them, so you may dial this number. All right, so that's the basic concept now, and then let's explain more the same thing in uh, more details or in another way. So again, so circuit basics. So as mentioned, perhaps in your other subject about electricity, and we're just recalling them here. So all electrical circuits require three elements. Now, as discussed a while ago, so we have the source voltage. Okay, so voltage source or source voltage, that is an electron pump. So it's just like an electron pump. Okay, it will push the electrons or the charges so that there will be a flow of electrons. So the flow of electrons is what we call electricity or current. So a source voltage, that is an electron pump, usually a battery or power supply. So this is we considered as energy in. So energy input, no? Energy input. Then the second element, we have a conductor. So a conductor is the element that will carry the electrons or the flow of electrons from and to the voltage source. So from and to the voltage source. So it will just go round and round in a closed path. So the conductor is often a wire. So here, what happens here is that there will be an energy transfer. All right, so there will be an energy transfer. So that is the scenario, class. And then the third element is what we call load. So load or resistance. So don't be confused, no? Because in your higher subject related to electricity, so normally word or term that is used more often is load. So it means that anything that consume or oppose the current flow, so that would be called as load or resistance. So a point where energy is extracted, a point where energy is extracted from the circuit. Sorry, this is from, no? From the circuit in the form of heat. So because this is from, this should be from. So it should be from the circuit in the form of heat, in the form of heat, light, motion, etc. So this is what we call energy out. So we have energy in, we have energy transfer, and energy out. So this is how you can think of uh, the three electrical, the three required elements in electrical circuits. Okay, so these are the basic concepts of circuit. Right, so another way of illustrating the concept is something like this. We have electron pump, or what we have called this a while ago as source voltage, so energy in. So electron pumps, so we have here electrons out of source, so there will be electrons inside here. Then this one is a pressure that will pumps out the electrons. Then the electrons will flow in the conductor. Okay, so electrons into load. So from the source, the electrons will be pumped out and it will flow into the conductor and it will go to the load. So load resistance, so energy out. So in this load, there will be energy that will be getting out. So in the form of heat, the form of light, or motion. And then we have electrons out of load. Then again, it will pass through a conductor. Then electrons back to source. Okay, so this is the flow of the electrons. And this is what we call the circuit. This is a closed circuit. So if a circuit is closed, then there will be a free flow of the electrons. So high energy electrons, on this part going to the left is high energy electrons. Then since some of the electrons are already out, the energy is out, so it means that the energy that will coming back to the source will be lower, no? In terms of strength or level. So the electrons that will go back to the source will be lower because there will be a loss of the electrons here because of the load that will consume that electrons, that will be transformed into heat, light, motion, or whatever. Okay, so the most basic electrical circuit look like this. Then potential changes of current in a circuit. It's something like this class. So high energy, then resistance. Because of this resistance, so there will be a potential drop. So when there's a potential drop, so what will happen is that the energy originally that was high, so it will become low energy. So potential changes of current in a circuit. So it means if you have a high current here passing through the load, so the car, because resistance is something that will oppose to the current flow, so what will happen, the flow of current here will becomes lower or less. Okay, so it will go back from the source, so low energy current, go back to the source, then again it becomes energized, so we have a high energy current. Okay, so it will just flow until all the source energy will be dissipated through the resistance. All right. Then potential rise across a power source. Potential rise. Okay, so we have here the source. So electrons get an energy boost. Okay, so this is the electrons gets an energy boost. Then electrons have more energy. So when electrons get out from the source, so high energy, so you have a high current here. So when you measure the voltage across this battery, okay, so you will have volts something like this. Okay, so high, so going to the right means high. Current, so electrons have less energy. When the electrons go back, so the current here will be less. So the reason is that so here originally the voltage is higher, okay, and then since the load already consumed, because there will be load here, there will be resistance here, so some of the energy or the current is consumed or dissipated in the resistance, perhaps the internal resistance of this voltmeter. For example, this is a voltmeter. So you will see that later that the voltage will drop, so there will be a drop in the voltage. Okay, so it means that there will be loss of the energy, loss of the energy in the resistor, because we have here the resistor, the internal resistance of this, we have the resistor. Or you can interpret this as when you have the battery. Okay, when you have the battery, when you measure the voltage, all right, so we have the voltage going to the right means high, and then when you try to measure the voltage uh, when you put the resistor, when you put the resistor across that voltage source, the battery, then you will see that the voltage will be lower. So because some of the energy is dissipated in this resistor, dissipated because it means consumed, no? The energy will be consumed because originally the current is very high and there will be opposition to that flow of the current. So what will happen to the current will become less. So we know that voltage, so from our basic concept, voltage is just the product of the current and the uh, voltage, sorry, resistance. Okay, so originally when the current flow out from the source, a very high current, but when it pass through the resistor, the current will drop, will become less because some of it will be consumed by the resistor or will be dissipated in the resistor. So there will be lower current. So the lower current here multiplied by the resistance. So that's why your reading here will be less. Okay, so in this case we have energy lost in the resistor. So electrons have less energy, then electrons have more energy here at this point. So measurable quantities that can be obtained from an electrical circuit. No? Measurable quantities. So what are those quantities that can be obtained from an electrical circuit? One is the voltage rise. So measures the energy given to electrons as they leave a voltage source. It is measured in volts. The second one is voltage drop. So measures the energy lost by to electrons when they leave a resistance. It is measured in volts. So normally given as negative. So this is a loss. Drop means loss. So that's why we have here a negative sign. Plus means rise. Then current is a measures or the measures that the flow, or sorry, current measures the flow rate through a conductor. it is measured in amperes, amps. A resistance measures the opposition to current flow through a conductor or resistor. It is measured in ohms. Its symbol is the symbol omega. No? The symbol omega. Okay, so this is the omega symbol. All right, so we have here electrical quantities. So 6.25 times 10 to the 18 electrons is equivalent to 1 coulomb. So remember this. And we know that 1 coulomb per second is what we call 1 ampere. So there are a lot of electrons class. No? 1 coulomb contains a lot of electrons. Can you imagine 6.25 times 10 to the 18? So when you type this number in your calculator, so that your calculator must have a very huge display so that it can be displayed properly in your calculator. So 6.25 times 10 to the 18 electrons. So that is equivalent to 1 coulomb. So remember this constant, class. So when this 1 coulomb passing through in 1 second, so we have what we call 1 ampere, because we know that 1 ampere is 1 coulomb, which is equivalent to 6.25 times 10 to the 18 electrons per second. So if there's a flow of electrons that is equivalent to this number, 6.25 times 10 to the 18 electrons passing through a certain point in 1 second, so we have a current that is equivalent to 1 ampere. Then we have what we call joule. So 1 joule, 1 volt is equal to 1 joule per coulomb. Okay, so remember this, 1 volt is equal to 1 joule per coulomb. So we have 1 joule is a product of 1 volt and 1 coulomb. So 1 coulomb of charge. So that is what we call 1 joule. Okay. And we have electrical meters. So electrical meters, usually called as ammeters. So these ammeters or ammeter is used to measure the current that is in amperes and are always wired in series in the circuit. Series in the circuit. So the wiring here is series in the circuit. And voltmeter measure potential in volts and are always wired in parallel in the circuit. So when you have a circuit something like this, okay, so if you have the circuit something like this and you have the voltage source something like this, so you put the ammeter, no, in series. So you have the ammeter, okay, so this is in series. So that is what is meant by this statement here. Then voltmeter measure the potential in volts and are always wired in parallel in the circuit. So parallel in the circuit. So if you have this circuit something like this, and you have here the resistance. So normally the voltmeter is here. That is connected in parallel. Okay, so this is what is meant by parallel. Wired in parallel in the circuit. So this is our circuit. It's connected in parallel. Okay, so an actual voltmeter looks like this. Okay, so we have here the actual voltmeter. It looks like this. We have the terminals here, the positive, the red for positive, the negative is in black. And actual ammeter, something like this. So look like this. That is what we call ammeter. The other one is voltmeter. Okay, then we have here electrical symbols class. So battery, normally we use only two. We have only two. but you can also have more. No, we have plus, we have this long, then short, long, short. So normally we have this symbol of the battery, but sometimes we use only uh, two. We have the long and then short, then we have the plus here, and this is a minus, so that will do also. Okay, then in wiring, so represented by this line, voltmeter, this is the symbol of voltmeter. Ammeter look like this, resistance, and this is the symbol. Capacitor, we have like this, and then this is bended. Then junction, so the junction is, then terminal, the symbol terminal. AC generator, we have variable resistance, so if you have the arrow, indicates variable. We have a capacitor here, and then you have the arrow, so it means that this is a variable capacitor. Now, relationships among electrical quantities in a current. So again, I'll discuss Ohm's law here in another way. So measure electrical quantities in an electrical circuit are related to each other by Ohm's law. So Ohm's law says if the source voltage remains constant, increasing the resistance in a circuit will cause a decrease in current in that circuit. In mathematical terms, it tells us that current flow is inversely proportional to the resistance. And in equation form, it says that voltage equal to the current I times resistance R, or volts V in volts equal to I in amperes times R in ohms. So again, this is Ohm's law class. Ohm's law, or can be written as V equal to IR. So the V here, this is the potential in volts or in joules per coulomb, or it can be the drop across the resistance. I here is the current in amperes, or we have coulomb per second. So this is the current passing through a resistor. And R here is resistance in ohms. So that is equivalent to volts per ampere. Volts per ampere, so that is resistance. Now, when you graph the voltage versus the current for a constant resistance, so you will see a straight line. Okay, so we have the vertical or the voltage, we have here the horizontal axis as the current. Okay, so we have here the change in current, and we have the change in the voltage. So resistance is just the change of the voltage with respect to the change of the current. Or rearranging, you will have delta V equal to delta I times R. So that is it means that the change in voltage, the change of voltage here is equal to the change of current multiplied by the resistance. So the resistance is constant and the current is changing. So the voltage also will change, no, according to the change of the current, because R here is constant. So you will see a straight line. This is the graph of the voltage versus current for a constant resistance. So we have here the slope, no? The slope of the line gives the resistance. So slope of the line. So what is the slope of the line in our calculus? So when you speak of slope M, that is the change of the uh, vertical part, no, vertical part. So if you have this change in V, for example, this is our change in V, and we have here the change in I. So if you take the ratio, no, if you take the ratio of the change of voltage with respect to the change of I, so you'll have the slope, no? Slope M, or slope is usually written as M. So slope M is equal to the ratio, equal to the ratio of the change in voltage with respect to the change of the current. So this is what we call the slope. Okay, So this is the slope. All right. So I hope it's clear with your class. Now, voltage sources and internal resistance. So all voltage sources contains internal resistance. So there will be internal resistance of any source voltage. That is resistance that is part of the voltage producing device itself, which cannot be eliminated. Of course, for example, for a lead acid battery. So lead acid battery has uh, um, a lead, no, a lead that also has a resistance. So uh, the the voltage will be, if you have the rating of that battery, for example, so what you will get is less than what is the rating because of the internal resistance. So the voltage that the device, say for example battery could produce if no internal resistance was present is called EMF. So EMF, electromagnetic electromotive force, no? If there is no internal resistance, so that is called EMF. Okay, so remember that. What is a electromotive force? So EMF stands for electromotive force. So the force that moves electrons. So if there's no, remember, if no internal resistance, so the voltage, we call it EMF. The usable voltage which is available to the circuit after the internal resistance consume its share of the voltage is called the terminal voltage. So remember this term, class, uh, because the internal resistance, there will be a voltage drop. So the original capacity or pressure of that battery, for example, is 100%. We call it EMF. But the voltage that will be available in the circuit will be less than that amount because of the internal resistance, which consume or oppose the flow of the current, and there will be voltage drop across that internal resistance. So that's why the voltage that is usable in the circuit is what we call the terminal voltage. So electromotive force, EMF, and the terminal voltage. So it's something like this, class. We have the conventional current flow. Okay, so negative to positive. All right, so we have here the EMF, electromotive force of source. All right, so you see we have this, when you measure the voltage, so we have this EMF voltage. But because of the internal resistance, this is the whole thing, class. This is a whole thing. So we have internal of this source, there is an internal resistance. Okay, just to understand more, so instead of putting it inside here, we just separate the internal resistance. But in reality, this one is inside the system. Okay, just to make sure, to make it clear, no, the explanation. So we put it apart, no, apart from this one, we put it separately. Okay, so when you take the, if there's an internal resistance, of course, current will flow in that internal resistance, so there will be voltage drop. All right, so there will be voltage drop. So when you measure from this end to this end, meaning from positive to negative, when you measure it, what you will see in the voltmeter, for example, that is what we call terminal voltage. Okay, so it's just suitable, no, because this is the terminal, this is the terminal, this is the negative terminal, this is the positive terminal, and when you measure the voltage from this terminal, negative terminal, to the positive terminal, so when you measure, uh, remember that voltmeter that is connected in parallel. So this is the source, and we connect the terminal of this voltmeter, for example, in parallel of this EMF. So parallel means if this is positive the EMF, this is also the positive of the voltmeter. This is the negative of the EMF. This is also the negative of the voltmeter. So they are now connected in parallel. Okay, so what you will see in the reading of the voltmeter, for example, that will be called, or that is called the terminal voltage. So terminal voltage therefore is equal to EMF which is positive, then plus internal resistance loss, which is negative, or in or we can say that EMF, we can write this as EMF is just the sum, no? The sum of the potential voltage. If you call the potential voltage as PO or PV, so potential voltage plus the or just to avoid confusion class, we will use sorry, EMF is the sum, no? The sum of the terminal voltage. So V T means terminal voltage, then plus the voltage drop, no? The voltage drop across the resistor. So you can also write in this manner. Or when you solve for the terminal voltage, simply terminal voltage V, we call it VT. So this is the difference. Now subtract both sides by VD, so we have EMF minus the voltage drop. So this is your EMF, then minus the voltage drop across the internal resistance. Okay, so you can also write the equation like this. Or we have here V terminal or terminal voltage is equal to EMF minus I times R. So because terminal voltage here is just the product of the this one is just a product of the the internal resistance, okay, multiplied by the current passing through that resistor or resistance. So that's why we have here, but take note this is internal. Take note this is internal resistance in the internal resistance class. Internal. Okay, so we have here voltage terminal is equal to EMF minus the product of the current and the internal resistance. Note that if R internal is very small, then a large percentage of EMF is available to the circuit. Alright, if this is very small. So if the material that is used in the electromotive force has less resistance, then almost 100% will be supplied to the circuit. Almost 100% of the electromotive force will be supplied to the circuit. Also note that if I, the current, is very large, then a large percentage of EMF is consumed within the battery itself, which can cause overheating and failure of the circuit. So this is generally the result of a short circuit. Okay, so remember this. This is very important class. If I, the current, is very large, then a large percentage of EMF is consumed within the battery itself, which can cause overheating and failure. Okay, so this result into a short circuit. So internal resistance and EMF. So we have here the battery, for example. So this is what I've mentioned a while ago, class. So EMF, that is the rating of this battery. Then because of the internal resistance, so we'll have here what we call the terminal voltage, because there will be a drop in this resistance here. So there will be when you measure this one, so there will be voltage drop due to internal resistance. Okay, so this is the voltage due to voltage rise due to EMF. Then we have the current flow. So net voltage rise of the cell. So it can be read here the net, meaning consider the two voltages here, the difference EMF minus the voltage drop. So that is what we call terminal voltage. Okay. All right. So that's the end of this part. And to see more details of the discussion, so you just look at the source of this material class from these references. All right. So we haven't done all the objectives stated in the objective class, but I have to cut the video at this point, and I will continue in another video, no, for the continuation of the next topic. Okay, so I'll end up this discussion here, part of the objectives of our lesson, and we'll continue it in another video, no, to shorten a little bit of our discussion. Okay, thank you very much, and see you again in the next video. Bye.